You're joining with the 2019 A-level structure is number 1. This question is not hard, right? It's not hard. It's like normal pattern. It's like going to the normal pattern. Okay, people, there are part A, part B, and part C in this question. Each part is divided into several Roman numbers. Lewis structures are there, resonance structures are there, and then you have the normal table which you're getting every year, and the same orbital naming you have, right? Okay, shall we start then? Part A, first one. Okay, part A, they are saying about the second row of the periodic table, right? Second row of the periodic table. So hydrogen, helium, then you have, I'll write them, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. This is what they're talking about. This is what they're talking about. Identify the element that has the highest electronegativity. People, you know, fluorine is the most electronegative. Why? Phone calls variation. We talked this in class. That means FONCLS, phone and calls CLS. So fluorine is the most electronegative atom in the periodic table in the second period. Actually, it's the most electronegative atom in the whole periodic table, right? You know that. Then second one, identify the element that has an allotrope which conducts electricity. You know, carbon. Carbon, people, forms something called graphite. This graphite, these carbon atoms are arranged something like this. 1, 2, 3, sp2 hybridized, and the other electron is free. So all of these carbons delocalize one electron into this electron cloud around it, and when you send an electric current through it, these electrons will conduct electricity. But if you take diamond, there are sp3 hybridized. There is another carbon attached. There is sp3 hybridized. So when you give electricity to this one, what happens is it will not conduct electricity. Why? Because there are no free electrons. Here, diamond, you have sp3 atoms, and graphite, you have sp2 atoms. This is a famous point in Unit 2 and also in inorganic. Okay, so you have carbon, right? That question, carbon is the answer. Next one. Identify the element that forms the monoatomic ion largest in size. This should be stable. People, the maximum number of electrons that an atom can gain and be stable is 3. Only 3 electrons, not maximum, more than that. So actually, people, you have F minus, O2 minus, and N3 minus. Let's take like that, N3 minus, and you have O2 minus and F minus. They ask in the one which has largest ionic radius. That means what? People, these are isoelectronic. I told you how to distinguish in between isoelectronics, right? It has largest negative is the largest size. Largest negative is the largest size. We talked about the theory behind this and how is this happening in the class. I won't go through that everything because this is a passive discussion. So this is the largest size, N3 minus. So there you have nitrogen, right? You have nitrogen. So first Roman number, it was highest electronegativity, that means fluorine. Then you had carbon. Then third Roman number, you had this nitrogen, right? Then what do they ask? Identify the element that has no p electrons but has a stable s configuration. People, stable s configuration means it has 1s2 or 2s2, 3s2, something like this. Stable s means the orbital is full, right? Orbital is full. That means it should be beryllium, right? It should be beryllium. And no p electrons also. Now these people also have S2 orbital filled, but they have p electrons. You can't consider that, right? So beryllium is the answer. You're going with that. Okay. Fourth one, beryllium. People next. Identify the element that has the highest first ionization energy. People, you know this. The ionization energy graph, we draw a ladder, right? We drew a ladder. Ladder, okay. One up, two down. One up, two down. One up, two down. Like that's only we discussed, right? So then people, it should be neon, right? Why? 1, 2, down. 1, 2, down. 1, 2, down. This is how we made neither. So what is this? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. They're asking from the second period. So neon is the answer. Right? Fifth one, neon. Fifth one, neon. Then people, last one then, sixth one. Sixth one. Identify the element that forms mostly electron deficient trigonal planar covalent compounds. Electron deficient, we talked about this BF3 structure. And they should be trigonal planar, right? Trigonal planar means that something like this we talked in the class. This atom is trigonal planar, right? It is trigonal planar. So what's the only compound which can form that? Boron. So 6 on, you have boron. Easy marks, right? Patta easy marks. Like you can score 100 out of 100 from this question. This one is easy. People then, next on Lewis structures thing we have. We have practiced a lot of Lewis structures in the class. Draw the most acceptable Lewis dot dash structure for the molecule SO3F2. You have sulfur, oxygen, 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 fluorine, and fluorine. People, when you have developed the ability of drawing Lewis structures and resonance structures, people, you don't need to do that method. You have method, I told you a method, I taught you a method, right? Total valence electron number, right? Then you add the charges if you have any, then you divide by 2, then you subtract the amount of bonds, then you have a certain amount of number of pair of electrons, then you put them one by one here and there, then you apply charges, then you neutralize the charges, then you have the Lewis structure. People, you don't have to do that always if you are good at drawing Lewis structures. People, this sulfur can exceed the octet. First thing you have to understand is that oxygen cannot exceed octet because it is a second period group. Sorry, second period element. Fluorine also can't. The fluorine double bonds are done, right? It's always single bond. People, sulfur, since it can exceed octet, we can draw bonds like this. Fluorine will not form a double bond, so it will stay like that. This oxygen lone pair, this oxygen lone pair, this oxygen lone pair, and this fluorine has 3 lone pairs. So sulfur 1, 2, 3, 4, 5, 6. No charge. This oxygen no charge, no charge, no charge, no charge, no charge. This is SO2F Lewis structure. SO2F Lewis structure. Then the next one, people. The most stable Lewis dot dash structure for the molecule H3N3O is shown below. Right. Let's draw that also. Let's draw that. What do we have? H. This is the question which I'm writing. N. Right. The most stable one is this one. Look. Okay, this is the most stable one. Draw 2 more Lewis dot dash structures or resonance structures for this molecule. Write the unstable, write unstable under the more unstable one. People, we can draw resonance structures. See, we can draw a lot of resonance structures. Out of them, we have to draw two and name the unstable one. Okay, people, we can do something like this. Here, lone pair to pi bond and then pi bond to lone pair. We can do that. So we draw the first structure like this. HO plus double bond, nitrogen. Then here single bond after removing the double bond. Then you have here minus, right? And then here NH3. Here you go. This is the first structure. This is the first structure which you can draw. Okay. Then there's another structure which you can draw. You can go from this side. You can go from this side. Lone pair to pi bond to lone pair. Lone pair to pi bond to lone pair. Make sure you draw this double-sided arrow. Without this, no marks. Without this arrow, you don't have marks for the resonance structures. And also make sure you put the lone pairs everywhere. If you miss a lone pair like this, that means no marks for the structure, right? So make sure you do them correctly. And also charges, mark the charges correctly. Hydrogen, because this question is easy, so they will check for everything. If you have missed something, then they will check for everything. Okay. This one minus then. Here nitrogen, double bond nitrogen, plus hydrogen. People, if I ask you what is the most unstable here, you should have an understanding about what we learned in class. There are two things which makes a structure unstable. I told you there are sins, right? Naraka deval, right? They are bad things to do. So having oxygen positive is one of them, and two equal charges on opposite atoms is one of them. People, here oxygen doesn't have a positive charge. That means the most electronegative atom doesn't have a positive charge. Here they have, so it's definitely unstable. Here there is unnecessary charge delocalization. I told you, like, that is the third thing which is like not much effective, right? This one we can consider it as stable, but not stable like this. This is the most stable. This is less stable. This is unstable. You can tell like that. They're asking you to write unstable, unstable under the more unstable one. So this is the most unstable, so you can write unstable here. So you can get all marks for this question here, right? See, very easy. Then people, next one very easy. Our table, I'll just read the answers there. Everyone can do it, I guess. I'll just read the answers there. People, here you have to first complete the structure. Now they have given a structure. Some years they won't give structure. You have to draw the structure and then you have to check for the answers. Otherwise you will get everything wrong. In paper class, let's practice this. People, Vesper pairs, electron pair geometry, shape or hybridization we have to check. Oxygen 1, there you can see VSC pair units 4, including the lone pairs 4. Then N2 will be 3. C3 is actually linear structure, so VSC pair units 2. N4 is having 3. Then electron pair geometry, O1 is going to be 1, 2, 3, 4, so tetrahedral. N2 is going to be 1, 2, 3, trigonal planar. C3 is 2, so linear. N4 is going to be trigonal planar likewise. Then shape, you can write either angular or V-shaped, or bent, you can write any of those three, correct? Same thing for N2 also. Then C3 linear, N4 trigonal planar. Hybridization, you know, if Vesper pairs is 4, sp3. Vesper pairs 3, sp2. Likewise, you can write. C3 is sp and N4 is sp2. Identify the atomic or hybrid orbitals formation of sigma bonds in the following dot dash structures. I told you sigma bonds are mostly formed from hybridized orbitals. It can form from unhybridized orbitals also. For example, H2 molecule, you have one hydrogen s orbital, another other hydrogen s orbital. So that's a orbital overlapping. Hybrid orbital overlapping, there are many examples like CH for this carbons sp3 hybridized. So that hybrid orbital is overlapping with hydrogen's s orbital. It can happen. Right? So most of the time it is always hybridized. So in this case, if you write the hybrid orbital for every answer, you're going to be correct. Count the Vesper pairs and then write the hybridization. Easy, right? Very easy if you write like that. Or else I can remember in the marking scheme they have given like for fluorine they have given 2p, that is also correct. Sometimes the terminal atoms will not undergo hybridization, we can consider it like that also. Sorry, 2p if you write that is also correct. Central atoms however definitely undergo hybridization, you have to consider the hybridization when you are writing. Okay. Then fifth one, people identify the atomic orbitals involved in the formation of following pi bonds in the Lewis dot structure. People always pi bonds are formed from p orbitals mostly, right? There are some occasions which can form from d orbitals. For example, consider this phosphorus people sometimes can form pi bonds. Sometimes it can form pi bonds, right? Sometimes this phosphorus can form pi bonds, and these pi bonds are from d orbitals, and these pi bonds sometimes are from d orbitals. You can't like, you have to know exactly, and I have taught in class how to do it. So the paper class, in paper class I'm going to teach you how to, like, I'll give you a question and then I'll make you get it wrong, and then I will teach you how to do it correctly. Paper class in the revision we did it something like this. Hari may worksheets තව දෙන්න තියෙනවා. First, for the first 2 units we have lot of more worksheets to be given. ඒ වගේත් මේවා අහුවෙයි. මේක දුන්නේ නැද්ද මන් දන්නේ නැහැ. I can't remember exactly whether I gave this or not. එතකොට මේක හම්බෙනවා. Once you get it, you'll exactly learn what is the difference there. So in this question all of them are going to be second group ne? So it is 2p orbitals, right? It is 2p orbitals. Okay then people, how are the two double bonds oriented in the Lewis dot structure? Some people might get this wrong. They are asking how are the double bonds oriented? Some people might write linear, that's all, right? Double bonds oriented in Lewis dot structure. Some double bonds around carbon. Around carbon you have double bonds. Some of you might write linear, but you won't get marks. Why? They're asking how the sigma bonds and pi bonds are oriented. That is what they're asking, right? Like this. Sigma bonds people, you know how they are overlapping. This carbon at the center you have. Let's take like this. Sigma bonds people always forms like this. Pi bonds, I told you, they are lateral overlapping. These curves are bending towards each other and they are forming a bond like this, right? They are forming a bond like this. So what happens people, they will form a circle. These electrons are going to circulate around these orbitals and these are like bending towards each other, right? This one and this one, they're like bending and overlapping with each other. So this one you call lateral overlapping. This is linear overlapping, right? This is linear overlapping, that is lateral overlapping. So either you can say the double bonds are perpendicular to each other. That means sigma bond and pi bond, they are perpendicular to each other. One is lateral overlapping, other one is linear overlapping. Or you can write like this. Perpendicular ලියුවත් හරි, or else you can write sigma bonds are linearly arranged and pi bonds are perpendicular, vertically arranged, horizontally and vertically. If you can write that, that one also you're correct. Then the second one, give an example of a molecule or ion that has similar orientation of double bonds. People, you can write CO2 also, CO2 or NO2 plus, whatever, you are correct. NO2 plus is like this. Then you have what? CO2 like this. Then that's it. Then people, C part first one. As atomic orbital is described by 3 quantum numbers n, l, m sub l, write appropriate quantum numbers and the name of the atomic orbital in the boxes given below. People, that question, some people got trouble with it. like how to do, we have discussed this in the class. There's an easy way to get everything. People, you need to know the equations, right? N is nothing, n value, n can be 1, 2, 3, you know that. People, then L value, what is L value? L is always less than and equal to n minus 1. And people, M sub L, it's going to be minus L to plus L. M sub S is always equal to plus or minus half. Okay, plus or minus half. People, if I say you n equal to, then n equal to, what is the value of L? What are the possible values of L? Possible values of L, people, it is 0 and 1. Why? N is less than and L is less than and equal to n minus 1. So what is n? 2. 2 minus 1 is 1. So you can have 0 as well as 1. Then M sub L minus L to plus L. That means you are taking the maximum value of L and you're counting from minus L to plus L. Right? So it is 1. M sub L, so therefore it is equal to minus 1 plus, minus 1, 0 and plus 1. Likewise, you have to do. M sub L, that means you are considering one orbital, right? One orbital. In one orbital, you can have two spins, clockwise spin and anti-clockwise spin. So M sub S can be plus half or minus half. Okay, plus half or minus half. Right, let's do that question now. First one, when n equal 3, sorry, not n equal 3. There is second one. First one, n is a box. Then you have L. Then you have M sub L. I'm saying like that, like M sub L. And then you have atomic orbital. You have the atomic orbital. They have given the atomic orbital. Make a box plus 1. Plus 1, 3p. People, this 3 means what? Energy level, 3, 3p means it belongs to the third energy level. This one is 3, right? Okay. So I told you when L equals 0, it means an s orbital. L equal 1 means p orbital. L equal 2 means d orbital. So p orbital means L equal 1, right? P orbital means L equal 1. And people, there are 3 p orbitals, px, pz, py. Px, pz, and there's another one going out of the plane like this. Px, pz, py, like that. Okay. Then people, next one, n equal 3, 2 minus 2. 3, 2 minus 2, they're asking this. People, 3 means that one should be 3. 2 means what? 3d orbital. Am I correct? Yes. 3d orbital. Next one. You have box, 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 and 2s. You have 2s, here box, here box, here box. People, 2 means n is 2. S orbital means L equals 0. Right? L equals 0. So S orbital, there's only one M sub L value. Why? M sub L is equal to minus L to plus L. So actually it's 0. So here also 0. That's it. That part also done. Then the next one, this variations we have discussed. Let's see what they have given here. Now you can stop the video and write these things. It's a video. You can stop the video and write anytime you want. Arrange the following in the increasing order of the property indicated in parentheses. First one, people, lithium fluoride, lithium iodide, and potassium fluoride. You have to compare the melting point. Melting point of ionic compounds. We have to look at what ionic compounds. These are not metallic bonds or anything. These are ionic bonds. Ionic bonds, people, we had to look at polarizing power and polarizability. I won't go into deep theory right now because this is a past paper discussion, so I'll take it very briefly. If you want to learn that, I have the study pack where you can buy it. You need to study pack which includes everything, variations and everything we have there. In the channel, I have all the details of the class given in some video, right? You can check the description of those videos. Or you can drop me a message in Telegram, our channel, you know, right? There you can join. Again, you can learn it, right? Not much like study pack, you don't think like it is 6,000, 7,000, just 2,000. Poti ganakata study pack you need to, right? Here, people, we have to look at the melting point of ionic compounds. You have lithium fluoride, potassium fluoride, lithium fluoride, potassium fluoride, and lithium iodide. What is the easiest way to get this? People, your periodic table you have. I told you this in the class. I'll do that. Do using that method. You keep the two hands like this. You keep lithium on this hand like this, and fluorine on this hand. Both are on top. Okay. Then potassium and fluoride. Then here. Then lithium and iodide. Then here. Like this. People, I told you, if the periodic table variation is like this, now you're looking like this. So if it was like this, then it is more ionic. That means melting point high. If it is like this, then melting point low. Why? It is more covalent. Polarizing power very high and polarizability very high and polarizing power low. Right? Polarizing power low. That means more covalent. This one more ionic. Right? Polarizing power is very less and polarizability also very less. Here polarizing power high, polarizability also high, therefore covalent. Right? So lithium fluoride is like this top. Okay, let's keep that aside. Lithium iodide, people, this is like more covalent. Potassium fluoride, more ionic. Most ionic, right? Most ionic. Then lithium fluoride like this. Actually, people, potassium fluoride is like this, then lithium fluoride like this, then lithium iodide like this. So if you think like that, you can directly get an answer within 5 seconds. What is the answer? Kf is the most ionic. So the highest melting point. Then you have lithium iodide is most covalent. Then in middle, you have lithium fluoride. Then the second one. Stability. People, in this stability, make a variation. Right? We don't have any variation to learn here. We are taking from like knowledge. You have done chemistry for like almost 2 years. You have seen structures. You can expect which is more stable. Stable ones are existing ones. Unstable ones don't exist. NF5 people, octet is exceeded. That's the most unstable. Right? Most unstable is NF5. You can see here, it is like patta unstable. Like this. 1, 2, 3, 4, 5. NF5. Very unstable. Right? So that is the most unstable one. They're asking the increasing order. Stability. Stability highest, then stability lowest is this one, NF5. Then people, you have NO4 3 minus, like this. This one. Have you ever seen a structure like this? No. This one, octet is okay. Everything is okay. But people, this structure is very unstable. Mega not unstable, like mecha unstable. Chuttak unstable, right? Little unstable. It's like in the middle. Then you have NO2 minus. People, NO2 minus, like this. You know this. This is nitrate. This is existing. This is very stable. You know this. So NO2 minus is the most stable, and then you have NO4 3 minus. NO4 3 minus here. Okay. Then the third one, bond distance. We discussed this in the class. Bond length variation, we discuss like magic, right? Magic. That is like patta. I love this bond distance variation. Let's see. NOCl. I won't go very deep here. You have NOCl. NOCl like this. There's a definite double bond here. Definite double bond. There's no resonance undergoing. There is a resonance that is unstable. NO2F. NO2F. Right? NO2F. They have given NO2F. NO2. Yes, like this. NO2F. Then people next on NOCl3. 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 Then you have to draw it like this. Otherwise you can't draw. Or you can draw it like this also. මෙහෙමත් වෙන්න බලන්න NOCl structure. NOCl3. Let's draw it like that. Then it's going to be good. Definite single bond. NOCl3. You have to think and draw this structure. කොයි වගේද එන්නේ කියලා පොඩ හිතලා බලලා අඳින්න ඕනේ, right? අර practice එකත් එක තමයි එන්නේ, right? From practice only you have to get. People now you can see this is a definite single bond. There is no resonance undergoing, so this should be the largest, right? NOCl3 is the largest. Then this is a definite double bond. Then this is the shortest. Definite double bond, so the shortest. In the middle is this. You can directly get the answer, but I'll explain you. People, these two pi bonds, this pi bond is like transferring from here to here. Actually, people, if we draw the resonance hybrid, it will be a cross, dotted line here. Dotted line here also, right? Dotted line here and dotted line here also, like this. Okay. Then what you do, you draw a square bracket and then you write the full charge. NO2F. NO2F, there's no charge, sorry. There's no charge. So this is how you draw, right? Or else you can do it like this. You can erase the square bracket and then write the resonance hybrid like this. Minus half, and here plus charge. Like this also you can write. People, here the pi bond, the bond order you have to find. The bond order here is, what? Sigma plus pi, sigma plus pi. What is sigma? Always 1 plus pi bond. People, pi bond can exist in two places in the class views. Like, is there a pi bond? Yes, papa. There is no pi bond. No, papa. We talked about that in the class. So pi bond probability of finding a pi bond in this oxygen, it is half. Like okay. You got a short method. We have to draw the resonance structures and we need to look at the pi bond probability of finding a pi bond. Then it is 3/2, 1.5. So people, here bond order is 1. Why? Sigma plus pi. Sigma only, there are no pi bond, so it is 1. Here sigma plus pi. 1 plus 1, 2. So from bond order also you can get a bond length. Okay, the people, then that question is done. 2019 question number 1, structure is number 1 we had discussed. Okay, then 2020, 2021, 2022, likewise we will move forward. Okay, do your work well. That's it. You never fail until you give up.